Hi everyone, welcome to Algebra 2, Lesson 6-3, Logarithms. In this lesson, you'll be able to evaluate and simplify logarithms. The lesson vocabulary are common logarithm, logarithm, logarithmic function, and natural logarithm. So we'll explore the logarithms today. Let's start with critique and explain. Earthquakes make seismic waves through the ground. The equation y equals 10 to the power of x relates the height or amplitude in microns of a seismic wave, y, and the power or magnitude, x, of the ground shaking it can cause. So if you look at the table over here, you have magnitude x and amplitude y given. So Taylor and Chun used different methods to find the magnitude of the earthquake with amplitude 5,500. So Taylor says 5,500 is halfway between 1,000 and 10,000. 3.5 is halfway between 3 and 4. So the magnitude is about 3.5. So he estimated it. Chun says y is equal to 10 to the power of x. 10 to the power of 3 is 1,000. 10 to the power of 4 is 10,000. And that means 10 to the power of 3.5 is about 3,162. 10 to the power of 3.7 is about 5,012. 10 to the power of 3.8 is about 6,310. So using calculator, he probably got different powers, right? And 10 to the power of 3.74 because we're trying to figure this out, right? 5,500. 5,500 is between 3.7 and 3.8. And so he's saying, oh, if it's about 3.74, it's about 5,500. So the magnitude is about 3.74. Okay, so looking at these two different methods, let's answer some questions. What is the magnitude of an earthquake with amplitude 100,000? How do you know? So looking at this, we don't have 100,000, but looking at the pattern, can you figure out what 100,000, what amplitude would be, what the magnitude would be for the amplitude 100,000? Well, we're looking at the powers, right? 10 to the power of what is 100,000? Well, your zeros represent the power of tens, right? So 1, 2, 3, 4, 5, magnitude of 5, because 10 to the power of 5 is 100,000. So an earthquake, let me type this. An earthquake with amplitude 100,000 has a magnitude of 5 because 10 to the power of 5 is equal to 100,000. Part B. Critique Taylor's and Chun's work. Is each method valid? Could either method be improved? So Taylor's method is a rough estimation, right? Chun is more accurate, obviously, but you do have to plug in one by one. That takes time. So we can write that. Taylor's method gives a rough estimate, but it is not valid if you need to find a more precise value. Chun's method, can you see this? Let me pull it here. So this is part B. Chun's method gives a much closer approximation, although guess and check method is not the most efficient way to solve problems because it's gonna take forever for anything that's more complicated, right? Yeah. So describe how to express the exact value of the desired magnitude. So we know from the equation that 10 to the x power is y. So 10 to the x power is 5,500. So the desired magnitude is this question mark, right? So the exact value of the magnitude is the value of x when 10 to the power of x is equal to 5,500. Yeah, so in this lesson, the lesson essential question is, what are logarithms and how are they evaluated? So now we feel a need to find a more efficient method. Can we solve this kind of question without guessing and checking all the time? Well, we know how to solve exponents. We know how it works and we understand exponents, but the inverse method of exponential equation would be logarithm, something called a logarithm. So let's explore the concept of logarithm. So example 1, understand logarithms. Solve the equations 2x equals 8 and 2 to the power of x equals 8. So for 2x equals 8, it's pretty easy. You can just use the inverse operation, divided by 2 to isolate x, right? And same thing for 2 to the power of x. Power is the inverse operation of log. So the inverse operation of exponents, so addition and subtraction, they're inverses, right? Multiplication, division, they're inverses. They cancel each other out. So the power or exponents versus log are inverse operations. So they have a relationship. Okay. So you can look at this equation. 2 to the power of x is equal to 8. So in order to solve this, you need an inverse operation, which is log. So log base 2, we have something called base, and then we have this number log of the log, which is equal to the result. So if we have an exponential equation, 2 to the power of x equals 8, we can see that the base will equal to the base of the log. So log base 2 of 8 is equal to x, which is the power. So you can convert exponential equation to log using this form. So solving this, you can plug it into the calculator if the numbers are more complicated, but you know that 2 to the power of 3 is equal to 8. So log base 2 of 8 is equal to 3. Okay, so yes, it takes a while for you to understand how it works. So here's the concept. The log base b of x is defined as log base b x is equal to y if and only if b to the power of y is equal to x. So these are the same forms, different forms, but same equations, just different ways to write it, because log and exponents are inverse operations. So when base is positive and not equal to 1, x and x is positive, you can use this. Okay, so this only works for all base that's positive and all x that's positive. So make sure your base and x are positive if you're using this function. So the log function y equals log base bx is the inverse of the exponential function y equals b to the power of x. So let's try number 1. We're not saying these two are the same, they're inverses, okay? Write the log form of y equals a to the power of x. Can you do this by yourself looking at this form? Okay, remember, base b to the power of y is equal to x, and it's color-coded here. Log base b to the of x is equal to y. No powers here, okay? So pause the video, see if you can change the form by yourself. Come back when you're ready for answers. Okay, are you ready? So, log, we need the base. Where's the base? 8. Log base 8 of x, which is the solution for the exponential function, which is y in this case. So make sure you write 8 in a smaller font. Log base 8 y is equal to x, the exponent. Okay, so looking at this concept, exponential and log form. Exponential form shows the base raised to the power of exponent equals the result c. And logarithm, using the same numbers, log to the same base a of the result c is equal to the exponent b. Okay, so we're using the same, we can use the same numbers in different forms in using log. So keeping that in mind, let's move on to example 2. Convert between exponential and log forms. Now we're going to practice converting the different forms more. So look at part A. What's the log form of 3 to the power of 4 equals 81? You change it to log form. Base is 3, exponent is 4. The result is 81. So log base 3, 81 is equal to 4. What's the exponential form of log base 10? 1,000 is equal to 3. Same thing, base is 10. So in exponential form, you write 10 to the power of, the result for log is the exponent. So 10 to the power of 3 is equal to 1,000. Okay? So it goes this way. So let's practice. Try number 2, A and B. What's the log form of 7 to the power of 3 is equal to 343? And what's the exponential form of log base 4, 16 is equal to 2? Pause the video, come back when you're ready for answers. Okay, are you ready? Let's look at part A. The log form would be log base 7 of 343 is equal to the exponent 3. And part B, what's the exponential form of this? Base 4 to the power of 2 is equal to 16, which is true. Okay, so check your answers. So if you got it right, if you did, good job. Let's move on to example 3. Evaluate logarithms. What is the value of each log expression? So let's look at part A, log base 5 to the log base 5 of 125. We don't know what the result is, but we can set that equal to x. And using it to and converting that to exponential form, base 5 to the power of x has to be 125, right? So we know that 5 to the power of 3 is equal to 125, so x is 3. So log base 5 of 125 is 3. So we can change forms and solve for it as well. Log base 1 over 4 of 16 is when you have 1 over 4 to the power of something that's equal to 16. In this case, we know the exponent has to be negative because we know 4 to the negative 1 power is equal to 1 over 4 by the negative property of exponent, right? So 1 over 4 to the power of x is really 4 to the power of negative 1. But that's just equal to 1 over 4, right? So changing that, let's see. 4 to the power of negative 1 to the power of x is equal to 16. So in order for you to figure out x, let's change all of this into the same base. 4 to the power of negative x is equal to 4 to the power of square, right? 4 squared is 16. So negative x must be 2, which means x must be negative 2. Okay, so use logic and equations that you already know. Log base 3 of 0 is when you have 3 to the x power is equal to 0. Can it ever become 0? No, there's no such power that it can make the base equal to 0. It can make it equal to 1, but never 0. Okay, so this is undefined. Okay, log base 2 of 2 to the power of 8. That's still fine. The result is still x that we're trying to figure out. So 2 to the power of x is equal to 2 to the power of 8, which means because the base is the same, your exponent has to be the same. X is just equal to 8. Okay, so let's look at try number 3. What's the value of each log expression? Pause the video, see if you can solve by yourself. Come back when you're ready for answers. Okay, are you ready? All right, let's look at part A. Log base 3 of 1 over 81 means you have 3 to the power of x, that's equal to 1 over 81. And obviously, this is going to have a negative exponent, right? Because 1 over 81 is the same as 3 to the power of negative 4. And so x is equal to negative 4. And part B, log base 7 of negative 7 means you need to find x such that base 7 to the power of x is equal to negative 7. In this case, could the base ever be negative? There is no power that has the power to make the base equal to negative. You can make it a fraction, but no, there's no power that can make it a negative 7. So this is undefined. Part C, log base 5 of 5 to the power of 9. So we need to find 5 to the power of x such that 5 to the power of 9 is equal to it, which means x is just equal to 9. Yeah. So those are the answers. Check your answers, see if you got it right. Great job if you did. Let's move on to this concept of common logarithms and natural logarithms. The base 10 log is called a common log, and it's written as log x with a base of 10 implied. So if you don't see any base when you see the log, that just means you have a base 10. It's implied. Okay, base e log is called a natural log, and if it's log base e, you'll never see this because we don't use that term. Instead, we just use ln. Okay, so that's just equal to ln, which is the natural log, ln x. Okay, so that's just the log with base e. The expressions log base 10x and log x just mean the same thing, just like ln e x and ln x. So they're the same thing. Okay, so ln is just like log, but it's implied that we have a base e. Okay, so because it's implied, we don't have to write that base. We can just use this because we use it a lot, probably. So let's look at example 4. Evaluate common and natural logs. What's the value of each log expression to the nearest 10,000ths? So log 900, if you plug it into the calculator, you'll see all of this. And so that's about 2.9542. And you can also check by calculating 10 to the power of 2.9542, which is about 900 as well. ln e means you have log base e of e. So if you plug it into the calculator, that's just going to be 1, because what is that? What is ln e? is log base e of e, right? So we're finding e of x such that that's equal to e, right? So it has to be 1. X has to be 1. So ln e is just 1. Okay, ln natural log of negative 1.87 is undefined because think about this. We're finding e to the power of x such that it's a negative 1.87. There is no power. E is a number like pi. Okay, so it's like an irrational number like pi. So if you plug it into the calculator, you'll see that E is equal to 2.71828182 dot and yeah, and it's never ending as well. And it is a positive number. And if your base is positive, no matter what your power is, you cannot get a negative solution, right? So this is undefined. ln of negative numbers do not exist. There cannot be a negative number for natural log ln. Okay, so these are some properties that the common and natural log have. So let's look at try number 4. What's the value of each log expression to the nearest 10,000s? So plug it into the calculator and let's see. Yeah, let's look at it right away. Log 321 is equal to 2.5065050032, and that's about 2.5061. We're going to round to the nearest 10,000s. Part B, natural log 1,215. If you plug it into the calculator, it's going to be 7.1024999356 ... and that's about 7.1025. Part C, log of 0.17 is going to be negative 0.7695510.786 ... so that's about negative 0.7696. Yeah, you're probably wondering, why do we have a negative result? Well, think about it. We're finding log base 10 to the power of x that's equal to 0.17. So 10, in order for it to have a smaller result than itself, you need a negative power because you need division, right? So it will never become a negative result. It will never have a negative result, but if you have a negative power, that means you have fractions like that. So yes, you may have negative results for log because your power can be negative. Okay, let's look at example 5. Solve equations with log. This is the fun part. What's the solution to each equation? Round to the nearest thousands. So 25 is equal to 10 to the power of x minus 1. Yeah, before we had to, it was really hard to solve with just the exponents, with just the knowledge of exponents, right? But now we know log. And so we can change this to the logarithmic form, which means the base is going to be log base 10, which is implied here, of 25 is equal to x minus 1. And now we have the variable x on a normal level, right? So on a base level. So log 25 is equal to x minus 1. And so x is equal to log 25 plus 1. And you can plug it into the calculator, which is going to give you about 2.398. Okay. Yeah, why? So some of you are wondering, if we're going to use the calculator anyway, why do we even need log? Well, why? Because even if you use the calculator, in order to figure out x, you have to plug it in one by one, and it's gonna take forever. Just like Chen's method that we looked at in the beginning of this lesson. right? So we don't want to do that. To save time, you want to use log and plug into the calculator just once, and then you have a nice little solution. Okay, part B, natural log 2x plus 3 is equal to 4. We know for this one, the base is e. So e to the power of 4 is equal to 2x plus 3, right? So plugging into the calculator, e to the power of 4 is about 54.598. You don't have to calculate it right now. It's actually more accurate if you solve for x first. So 2x is equal to 2 to the power of 4 minus 3, and so x is equal to e to the power of 4 minus 3 all over 2. So if you plug it into the calculator, just like this at the end, then it's going to give you a more exact solution, which should be about 25.799. All right, so now learning that, let's try number 5, pause the video, see if you can solve these equations by yourself. Come back when you're ready for answers. Okay, are you ready? Let's look at part A. So we have log 3x 2 is equal to 2. What's the base here? There is no base, which means base 10 is implied. So 10 to the power of 2 is equal to 3x minus 2. 10 to the power of 2 is 100. So 100 plus 2 is equal to 3x. X is equal to 102 divided by 3. Which is 34, right? Yeah. So x is 34. You don't have to even round up. Part B, e to the power of x plus 2 is equal to 8. So that means this is an exponential form. You want to change it to a log form, right? So log base e of 8 is equal to x plus 2, which means that's the natural log. Ln 8 is equal to x plus 2. So ln 8 minus 2 is equal to x. So if you plug it into the calculator, it's going to be about 0.07944154168. So that's going to be about 0.079, rounded to the nearest thousands. Yeah, so another way is to change the form into another form, or you can put ln on both sides and make it ln e x to the power of x plus 2 is equal to ln 8, and then change it, but that's going to give you more steps, so just change the form right away. All right, let's look at example 6. That's the last example we have today. Let's use logarithms to solve problems in real life. Let's look at this example. The seismic energy, X, in joules can be estimated based on the magnitude, M, of an earthquake by the formula X equals 10 to the power of 1.5 M plus 12. What's the magnitude of an earthquake with a seismic energy of 4.2 times 10 to the power of 20 joules? So you're going to substitute this to the seismic energy. Seismic energy is represented by X, right? So you plug it in to this equation in substitute of X. And then you'll get this formula. And you're solving for M because that's the magnitude, right? So solving for this equation, you need log to solve it efficiently. So log base 10 to the power of this. Log base 10 of the result is equal to the power, right? So log, you don't have to write the base, of base 10 of 4.2 times 10 to the power of 20 is equal to 1.5 m plus 12. So this minus 12, all of that divided by 1.5 is m, which is about 5.75. So yeah, that's it. So you just have to change the form, solve for the variable, and plug it into the calculator. you need a calculator. Yes. Try number 6. What's the magnitude of an earthquake with a seismic energy of 1.8 times 10 to the power of 23 joules? So it's the same thing. See if you can solve it first. Pause the video and come back when you're ready for answers. Okay, are you ready? So you're using the same method. You're going to plug it into the formula and set up the formula. 1.8 times 10 to the power of 23 is equal to 10 to the power of 1.5 m plus 12. And so log base 10 of 1.5, no, log base 10 of 1.8 times 10 to the power of 23 is equal to 1.5 m plus 12. And so log of 1.8 times 10 to the power of 23 minus 12, all of that divided by 1.5 is equal to m. And plug this into the calculator. Don't forget the parentheses. They're important because if you don't plug it in, calculators don't really know which order they should do first, right? So make sure you tell the calculator. And that's about 7.503515003. So the magnitude is about 7.5. Okay, so check your answers if you got it right. If you did, good job. And that's the end of our examples today. So let's summarize our lesson. We learned about logs, right? Logarithms. So logarithm is the inverse operation of the exponents, the power. So we can change the form between exponential form and logarithmic form to write the same equation. So using exponential form, we have base b to the power of x equals y, the result y, which is the same as the logarithm form, log base b of y is equal to x. Okay, so that was lesson 6-3, logarithms. We'll continue with the next lesson in the next video. Thanks for watching.